Beta, in my last class, I thought I told you that whenever we are moving in 3D series from scandium to zinc, the atomic and ionic radii first decreases because of the increase in nuclear charge or effective nuclear charge. But after the midway, the shielding, screening, or repulsive factor will try to counterbalance the nuclear charge or effective nuclear charge. That's why the atomic radii after the midway become constant till copper. And at the end, due to interelectronic repulsion, I said the size or atomic radii, the size will enhance. This is what we have done. Now the question is, suppose if I have this series now, this is the 3D series, this is the 4D series, and this is the 5D series. What will happen to the atomic and ionic radii if I'll try to move from 3D to 5D or 6D series, 3D to 4D, 4D to 5D series, or 6D series? Of course, beta, the atomic and ionic radii will increase. Now the question is, sir, why does the atomic radii increases while we are going from 3D to 4D or 4D to 5D? The answer is very simple, that in case when we are talking about 3D, this is suppose 3D. This is suppose the nucleus. When you are adding an electron into the 3D series, then the electron goes to 4D series, and then electron goes into the 5D series. So at each successive level, the size is increasing, or the size of the 3D shell is increasing. That's why the atomic or ionic radii will of course increase. So I have written the atomic radii increases while down in each group. But the most important thing which I have to take up right now, of course, is the concept of lengthenite contraction. Peter, what I was trying to tell you is, suppose this is 3D series, this is 4D, and this is the 5D series. Although I said that when you try to go from 3D to 4D and 4D to 5D, there is a there is an increase in atomic radii. But the most important thing is there is a huge jump in between 3D and 4D in the atomic radii, as you can see from the data also. But the point is, the 4D and 5D series element have almost the compatible atomic radii, or has almost the same atomic radii, or there is almost negligible jump between the 4D and the 5D, or the second and the third transition series. And this is actually because of lengthenite contraction. Whenever you are talking about case based question, अगर आप case based question की बात कर रहे हो, या whenever you are talking about paragraph based question, the question is asked from here. As you can see from here, I have written very clearly the 4D and the 5D, or the second and the third transition series, has almost the same property because of lengthenite contraction. So I have to now take up that what is basically lengthenite contraction is, and of course what is the reason for lengthenite contraction. But I must tell you, beta, what exactly I was trying to tell you is, because of lengthenite contraction which is present in the second and the third transition series, or the 4D or the 5D series, zirconium and hafnium, niobium and tantalum, or molybdenum and tungsten has almost the similar property, and it is all because of what lengthenite contraction is. ये जो भी कुछ है, ये सब lengthenite contraction की वजह से ही है. So right now the concept is that, sir, what is basically lengthenite contraction is? Let's understand the concept of lengthenite contraction. Although, as I said, it is there in F block also, but still, let's start. See, if I am talking about the journal electronic configuration of F block element, that is n minus 2 F1 to 14, n minus 1 D0 to 1 NS2. ये F block element का journal electronic configuration होता है. I still remember when I was teaching you the basics, जब मैं आपको basics बता रहा था इस periodic table का, तो मैंने आपको बताया था when we are talking about n is equal to 6, जब हम n is equal to 6 की बात करते हैं, तो इसमें फिल होता है 5D सीरीज. 5D सीरीज इसका पहला एलिमेंट होता था lanthanum. But I thought I said very clearly, before the 5D fills, of course, in lanthanum, which is the first element here, before the 5D fills, ऑफबो प्रिंसिपल बोलता है कि 5D जो होता है उससे पहले हमें 4F को फिल करना चाहिए. सो दैट्स वाई 4F सीरीज में अगर देखा जाए तो लेंथनम से पहले, लेंथनम के बाद सीरियम जब फिल हो रहा था, यानी लेंथनम में अगर 5D फिल होता है तो उससे पहले 4F फिल होना स्टार्ट होता है, यानी 4F के पहले 14 एलिमेंट्स फिल होंगे, फिर 5D के हैफनियम 72 से स्टार्ट होता है फिल होना. सो इफ आई ट्राई टू अप्लाई द सेम कॉन्सेप्ट ओवर हियर, अगर मैं यही सेम कॉन्सेप्ट यहां पर अप्लाई करने की कोशिश करूं, तो व्हाट आई वांट टू टेल यू इज कि अगर मैं n इजिकल टू 6 ले लूं तो इसमें क्या होगा, ये 6s हो गया, ये 5D हो गया और ये 4F हो गया. और अगर मैं इसे यहां रखना स्टार्ट करूं, ये मेरा 4F है. मैंने इसे डॉटेड से इसलिए बनाया क्योंकि 4F हैज अ पुअर, नहीं वेरी वेरी पुअर शील्डिंग इफेक्ट. और ये 5D है, 5D को भी मैंने डॉटेड से बनाया, इसका मतलब इसका भी स्क्रीनिंग इफेक्ट बहुत पुअर होता है. और ये मैंने 6s बनाया. अब अगर मैं पहली डेफिनेशन लेंथेनाइड कॉन्ट्रैक्शन की आपको ये बोलता हूं कि the filling up of the 4F orbital before the 5D orbital that result into a regular decrease in atomic and ionic radii of the inner transition series or 4F series is basically called as lengthenite contraction. तो डेफिनेशन पे तो पूरे मार्क्स मिल जाएंगे. Now the question is why, sir? Why? As I said, when you try to move from 58, 59, 60, 61, 62 till 71, the nuclear charge is increasing. And nuclear charge increase hota ja raha, hota ja raha, hota ja raha. But the problem right now is the shielding effect of 4F subshell is very poor, very, 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 very poor. And 5S, 5D is also poor. So nuclear charge बढ़ रहा है, मगर 4F और 5D इस न्यूक्लियस को शील्ड नहीं कर पा रहे. तो लास्ट वाले 6s इलेक्ट्रॉन को बहुत स्ट्रांगली न्यूक्लियस अगर अपनी तरफ पुल करेगा तो एटॉमिक और आयनिक रेडियाई डिक्रीज होगा. दिस इज व्हाट आई वाज टॉकिंग अबाउट, दैट दिस इज एग्जैक्टली कॉल्ड एज व्हाट लेंथेनाइट कॉन्ट्रैक्शन इज, कि फिलिंग अप ऑफ द 4F ऑर्बिटल before the 5D resulting into the decrease in or atomic radii और ionic radii is called lengthenite contraction. और इसका रीजन बिल्कुल सिंपल सा है, इट इज ड्यू टू द पुअर शील्डिंग इफेक्ट ऑफ द 4F subshell or even 4F and 5D both. That's called lengthenite contraction. So the atomic and ionic radii decreases down the group. However, as I said, the jump in between the 4D and 5D, yani the second and the third transition series is almost negligible, or inka atomic or ionic radii is almost constant, and it is all because of lengthenite contraction. तो मैंने इसकी explanation ये दी, the size decreases down the group due to introduction of an additional cell at each successive level. That is clear. But nearly equal radii of second and third transition series is due to a special effect which is called lengthenite contraction. Definition we have already done. As a result of this, as I said, the most important thing is the question which is asked is that why do zirconium and hafnium, as I said, the question is very clearly asked in the paper, why do zirconium and hafnium, niobium and tantalum, and molybdenum and tungsten shows almost similar physical and chemical properties? It is because of lengthenite contraction, or their atomic radii almost are same. Or the question can be even put in this way, why do 4D and 5D or the second and the third transition series almost have same atomic radii? Again, the answer is same, because of lengthenite contraction. So if you go through, I have already written these questions when I have discussed the question and answer, and that is, why do second and third transition series or zirconium and hafnium shows similar physical and chemical property? Of course, one line answer, that is because of lengthenite contraction is. Now, lengthenite contraction is clear. Beta, my next property is, of course, the most important topic, that's called enthalpy of atomization. And on the basis of that, of course, I'll be discussing the metallic character also. See, the point right now is, what is enthalpy of atomization is. See, when we are actually trying to convert a molecule into corresponding atoms, that's basically called as enthalpy of atomization is. अब जो डी ब्लॉक एलिमेंट होते हैं, और द डी ब्लॉक एलिमेंट और द ट्रांजिशन एलिमेंट, दे हैव अ ह्यूज enthalpy of atomization. So the question which we have to discuss right now is, transition metal exhibit higher enthalpy of atomization. Question is why? Why do they have a very high enthalpy of atomization? And as I said, on the basis of this, it has the highest, or all the properties will be discussed on the basis of enthalpy of atomization. See, as we have already done that ns and n minus 1d, when we are talking about ns and n minus 1d subshell, they almost have compatible or comparable energy. I repeat, in transition element, we have already done that the 3d as well as the 4s has comparable or compatible energy. When they have a compatible or comparable energy, of course, if the suppose this is the d subshell, this is the d subshell, there will be more number of unpaired electrons, and beta, more the number of unpaired electrons means greater will be the frequent metal metal bonding in this. And if there is a greater or frequent metal metal bonding in this, they will have stronger metallic bonding, and that's why they have a stronger enthalpy of atomization. What I mean to say right now is, due to the compatible energy, short to the point, due to the compatible energy of ns and n minus 1d in, of course, transition element, they have unpaired electrons. And I have already done what, there is a stronger interatomic metal metal interaction. इसका मतलब डी ऑर्बिटल्स में बहुत स्ट्रॉन्गर मेटल मेटल बॉन्ड बनेगा या इंटर एटॉमिक बॉन्ड बनेगा, और इस वजह से दे हैव अ वेरी हाई इंथैल्पी ऑफ एटोमाइजेशन. So transition element have a higher enthalpy of atomization because of stronger interatomic metal metal interaction or stronger metallic bond. That's it. This is more than enough. Now the question is, what will happen to the number of, suppose if I'll try to go from 3D to 4D, 4D to 5D series. See, if I'll try to go from 3D to 4D, 4D to 5D series, I'll find that, as I said, this is 3D series, this is 4D series, this is 5D series, this is the nucleus. As you go away from the nucleus, what will happen? The number of unpaired electrons can be made quite easily. यानी मैं बहुत आसानी से अनपेयर्ड कर सकता हूं. यानी 3D में अगर 4 अनपेयर्ड इलेक्ट्रॉन है, 5 है, तो 4D में बहुत आसानी से अनपेयर हो सकते हैं, बिकॉज इट इज क्वाइट अवे फ्रॉम द न्यूक्लियस. एंड 5D तो इट इज ऑलमोस्ट वेरी इजी. So that means there will be frequent metal metal bonding possible whenever we try to go from 3D to 4D and 4D to 5D. इसका मतलब enthalpy of atomization जो होगी वो increase करेगी. So I have written this point here, that is 4D second transition series and 5D यानी third transition series shows a greater enthalpy of atomization as compared to 3D transition series because of larger size of 4D and 5D. It means there will, or it will have more number of unpaired electrons, and more frequent metal metal bonding will be possible in them, and that's why they have a higher enthalpy of atomization. Now, as I said, all the properties depend upon enthalpy of atomization. For example, melting and boiling point. So when I'm talking about melting and boiling point, they have a huge melting and boiling point. Why? Again, of course, it is, if you ask me why they have a higher melting and boiling point, I'll say the same answer, that since enthalpy of atomization of transition element is very high, that's why they have a high melting and boiling point. Now, as I said, the enthalpy of atomization as well as now the melting point will depend upon what? The number of unpaired electrons. That means greater the number of unpaired electrons, greater will be the what? Metallic bonding, and greater will be the enthalpy of atomization, higher will be the melting and boiling point. So the point right now is, अगर मैं 3D series की बात करूं, if I try to talk about 3D series, what will happen when you try to go from what? As I said, when you try to go from scandium to Mn, Mn will have the maximum number of unpaired electrons, and that's why Mn should have the highest enthalpy of atomization, and of course higher melting point. but there is an exception. There is no exception as such. The concept is something. As I said, enthalpy of atomization or melting and boiling point depend upon enthalpy of atomization. And enthalpy of atomization depend upon what? Number of unpaired electrons, right? As the number of unpaired electron increases, what will happen? Enthalpy of atomization increase, melting point also increases. And we have already discussed. But now the point is, if you go through this diagram, you can easily make out from here, इस डायग्राम को या इस ग्राफ को देखा जाए तो एटॉमिक नंबर को प्लॉट किया गया मेल्टिंग पॉइंट के साथ. तो अगर एटॉमिक नंबर को मेल्टिंग पॉइंट के साथ प्लॉट किया हुआ देखा जाए तो आपको क्या दिख रहा है? मैंगनीज के पास मैक्सिमम नंबर ऑफ अनपेड इलेक्ट्रॉन्स होते हैं, यानी इंथैल्पी ऑफ एटोमाइजेशन हाईएस्ट होनी चाहिए इसकी. प्रॉब्लम है बेटा, इसकी इंथैल्पी ऑफ एटोमाइजेशन कम होती है और आप देख रहे हो क्रोमियम की ज्यादा है. अगर आप इसी तरीके से अगर ये 3D की बात कर रहे हो तो ये 4D सीरीज है और ऑफ कोर्स ये 5D सीरीज है. तो यहां पर अगर मैंगनीज का हाई है होना चाहिए था तो टेक्नीशियम का भी और रेनियम का भी हाई होना चाहिए. बट आप देख पा रहे हो बेटा, द पॉइंट इज chromium has a higher enthalpy of atomization in this group 3D, molybdenum, and of course the rest. So what I mean to say is, in the 3D series, chromium has a higher enthalpy of atomization or melting point than manganese. Now what is the reason for it? Which of course most of the books are writing in an incorrect way. So I have written here, understand the point. Chromium with 5 unpaired electron in 3D series shows higher melting and boiling point greater than Mn, because Mn is already stable in half filled electronic configuration. So it won't go for what? Interatomic bond formation. That means anything which is already stable, why it is going to go for what? Interatomic bond formation. There is another point. Remember beta, the more the delocalization, the more the stability and more will be the strength of metallic bond. That means if there is more delocalization of electron, the greater will be the stability of what? The stability of the atom, and greater will be the metal-metal bond formation. You will find that this is seen in case of chromium and not in the case of what? Manganese. कहने का मतलब मैंगनीज के जो इलेक्ट्रॉन्स हैं वो डीलोकलाइज नहीं होते हैं, दे आर ऑलरेडी स्टेबल. बट व्हेन वी आर टॉकिंग अबाउट व्हाट, व्हेन वी आर टॉकिंग अबाउट chromium, the electrons are more delocalized, they are more stable, and they have more metallic bond formation, greater stability, and that's why they have greater enthalpy of atomization, as well as they have a higher melting and boiling point or melting point. But let's talk about zinc, cadmium, and mercury. As we have already done, zinc, cadmium, and mercury, they do not have any unpaired electrons. So that means their melting and boiling point will be very, very low, or their enthalpy of atomization will be very, very low. They will always exist in liquid or semi-solid state. So this is sample paper 2008 ka question, which of course is written here. Due to the above reason, which as I said, they have a completely filled electronic configuration, zinc, cadmium, and mercury, they are either soft in nature or they have a low melting and boiling point. The reason is very much clear, because as I said, they have fully filled electronic configuration. They do not have very high value of enthalpy of atomization is. Beta, now we are going to the topic which is called density. See, transition element have a higher density, right? As we have already done that the transition element, when you try to move from left to right in 3D series, the density will increase. See, we know that what is density is. Density is nothing but it is mass upon volume. अब आप खुद सोचो बेटा, when the electrons are being added into this shell, 3D shell में add हो रहे हैं, और यहां देखो बेटा इलेक्ट्रॉन यहां ऐड हो रहा है, न्यूक्लियस अपनी तरफ इस क्लाउड को, इलेक्ट्रॉन क्लाउड को पुल कर रहा है अपनी तरफ. तो इसका मतलब क्या हुआ? वॉल्यूम कम होती जा रही है. तो अगर वॉल्यूम कम होगी और मास बढ़ती जा रही है बेटा, so that means the density will increase. So when you try to move from left to right, as I said, the density increases from left to right due to the low atomic volume, due to the addition of electron in n-1d subshell. What I said, the electron is added here in this shell. So volume is not increasing. In fact, the volume is decreasing, but mass is increasing. So when mass per unit volume is increasing, or I said mass increases, volume decreases, so density will also increase when you try to move from left to right. But when you go from 3D to 4D, 4D to 5D, the volume increases. Volume increases means density will decrease. That's it. This is the concept.